Okay, so I'd like to welcome Dr. Carl Wallace to Chemistry 108. He's going to tell us a little bit about the research that he does in his lab, and then I will ask him a few questions that you as the student might be interested in knowing if you decide to pursue undergraduate research in his laboratories. I'll turn it over to you, Dr. Wallace.
Okay, well, thank you very much, and welcome to everybody in Chemistry 108. And as Dr. Masterson said, my name is Dr. Wallace. I am the token inorganic chemist of the department. I actually classify myself as an inorganic stroke supermolecular chemistry. At your level, I'll appreciate that you probably don't understand what supramolecular chemistry is, so I'm not going to focus too much on that particular aspect of my work, but we'll really just talk about my broad interests in the chemistry world. So you can see at the very top here, I've got a very broad general title that says low molecular weight fluorescent probes. So in the broadest sense, I like to make sensors. And these sensors can fall into three major categories. And the ones that I'm just going to talk about with you guys today are basically anion recognition, cation recognition, and neutral molecule recognition. I won't talk about the nanochemistry or the material side of it. That's being developed as we speak. I'm just going to keep our discussion mainly to the core concepts or the core areas of my research. So as you guys probably already know in your chemistry life is that we have anions. And so remember what anions are. These are negatively charged species. All right. We have cations. These are positively charged species. We have neutral molecules as well. And these are these three, I should say, pretty much make up 100% or nearly 100% of all of them kind of the molecules in terms of charges or neutral species that we see in our lives. And so why are these important? Well, we'll talk about these one at a time. So we've got anion recognition first. I'm specifically interested in anything that could be of an environmental or biological importance. Okay, so if we build up, say, for example, phosphates or nitrates in water systems, all right, we can have a process that might occur, which is called eutrophication, which is the build-up of algae, essentially, in lakes. So there's a lot of interest in making sensors that are either colorimetric or fluorescent. So that's what I do mainly, is optical spectroscopy. Okay, so can we make small molecules, all right, and I call these LMFPs, so small molecules that can change their optical properties based on either anion recognition and cation recognition or neutral molecule recognition. So I'm going to give you two examples here. This is some very early work. I like to call this one my Venus flytrap. So you can see here we have a Venus flytrap whereby we have a spherical anion that's coordinated inside this molecular probe. This one actually was not a colorimetric system. It was actually an electrochemical system. But you can see here we have this anion that's encapsulated, just like the Venus flytrap encapsulates its fly once it's caught in there. I'm also interested, being the token inorganic chemist, I'm also interested in looking at the recognition and the binding of toxic metals. So they could either be ferric, okay, cadmium, mercury, and lead. All right, and we've all heard of potential lead poisoning in our water systems around local municipalities around the country. The most famous one is the recent situation up in Flint, Michigan. And so monitoring the amount of lead or even any of these kind of toxic metals in the environment is an area of interest for me. Not just necessarily in the environment, but also in our biological systems. So, for example, looking at zinc and ferric ions as well in biological applications, and we especially in systems known as labile ion pools. I'm not going to go into the details about what is a labile ion pool, but I'm interested in looking at making molecular probes that we can incorporate into the cell, and we can do some cell imaging with these molecular probes. And then a very recent project that I've got going is looking at drugs and psychoactive compounds and detecting new psychoactive compounds. Actually, we call these NPSs, and these are a big problem on the streets of America at the moment, and that's because these are stimulants, I should say, beg your pardon, which have MDMA type properties, and there's a real interest in detecting these guys. The problem is that these are neutral molecules, and making molecular sensors for neutral molecules is a little bit more challenging than charged species such as anions or cations. So in a nutshell, that's basically what I like to do. So I kind of consider myself a bit of a jack of all trades in the chemistry world, which is basically I do a little bit of organic synthesis. By no means am I an organic chemist, but I like to make these small molecules. Okay, so these small molecules are typically going to be organic frameworks. And so we have to synthesize a lot of these organic frameworks. And because I'm an inorganic chemist, I like to incorporate metals as part of these molecular probes as well, because they give rise to some very interesting optical properties. And so sometimes I'll make receptors that have metals in them as well as part of the sensing motif. Making materials, but I'm not going to talk about that one at the moment. And so why do I have a picture over here of a hydrangea? And that is because I deal with colorimetric systems. This is a beautiful example of a naturally occurring colorimetric system. And in fact, the color, whether or not you've got pink or blue, is dictated by how acidic or basic your soil is. So I always like to put that one in as an example, as I deal with a lot of color chemistry. So this is essentially, if you will, a pH sensor, which I'm sure you guys are all familiar with at your level. Anyway, that's it for me. Okay, so I've given you just the broadest aspects of my work, which basically deals with sensing small analytes.
Fantastic. Well, thank you, Dr. Wallace. Just to let you know, we do have a number of students in Chemistry 108 who are thinking about med school. We have a number of students who are also thinking about being process chemists or being associated in some form or fashion with forensics. Can you talk a little bit about how people who are interested in those things might be able to fit into your lab as an undergraduate researcher?
Sure. So I'm always interested in taking undergraduate research students in my lab. And you can probably tell that a lot of the interest that I have can stem into the fields of either medically orientated work or forensics work as well. And we'll deal with both of those separately. And so in the medical world, imaging is extremely important. Okay, so if we're looking at trying to look at specific targets such as zinc or copper that can undergo, I'm sorry, let me take that back, iron and copper that can undergo Fenton chemistry. And Fenton chemistry is the generation of free radicals. And you've probably heard that free radicals cause cancer somehow or another in our body. Okay, and you may have heard about that in your careers. And we want to monitor the amount potentially of the metal in there, or even the free radicals that are being, because we can make radical traps as well. And we can use imaging processes to give us an understanding of that process. Okay, so that's how we can use or potentially use my work in the medical application. So it might have an interest for those in the medical field. For those that are in the forensics, anything to do with sensors, okay, is a natural fit for those people that want to go off into the forensics world. In fact, I've currently got two forensics majors in my lab at the moment. One of them is making small molecules for the recognition of hazardous waste material for metals. So she's making these small receptors looking at mercury, cadmium, and lead. Okay, specifically. So she has an interest in making these molecules or sensors for environmental purposes. And then I've got another forensics major who's actually going to start working on detection of drugs. Okay, so she's interested in the forensics aspect, and she's going to be working on looking at NPS type molecules and cathinone derivatives, etc., etc. So naturally, the work that I do certainly fits into the realms of, for those students that have an interest in the biomedical aspect and also forensics aspect as well. And if you're just interested, maybe you want to go into industry and do some kind of quality control type work in industry, because a lot of pharmaceutical companies, they need people to do quality control, and really a lot of that is analytical chemistry. Okay, so we do a lot of analytical chemistry as well in our lab when we're making these kinds of sensors. So absolutely, if you've got interest in the medical world, the forensics world, or even industry, the work that you would do in my lab will certainly be able to set you up for one of those fields.
Well, fantastic. Thank you for that. Could you talk a little bit to the students about when you typically like to have students come and join your lab? What stage of their undergraduate career?
Sure. So I actually like to take students when they've got very little experience. I don't mind taking the risk of they've basically had no chemical experience, no hands-on wet, with the exception of your general chemistry labs, maybe, that you're currently already doing. That's the only experience that you've had. But I like to take students as early as possible, because that gives them the opportunity to really develop a nice project over the course of, say, maybe 4 semesters. I've had students in my lab that have actually done like 5 semesters with me during their chemistry career. They've started in my lab essentially as a freshman, maybe in their 2nd semester of their freshman, but more often than not, they come in kind of at junior level. I certainly, and this is a personal preference, I really would like them the sophomore, junior level. Junior are absolutely the latest, because if you're doing a chemistry degree as part of the ACS degree, as part of your capstone course, you have to do, and I'm sure Dr. Masterson's already explained the milestones of our capstone course. You have to do 496, CHE 496. But I always like to have students come in way before they do their 496 so they can develop their project. So that was a long-winded answer to Dr. Masterson's question. Basically, the sooner the better. And I would take students in pretty much any time. The only thing that kind of will stop me from taking students is if I just don't have room. Okay, and I'll be honest with you. So the way that I do it in my lab, it might be a little different from other faculty. I like to pair my graduate students up. So at the moment, I have 3 graduate students with at least 1 undergraduate to start with. And when the graduate student is more comfortable, they can handle more undergraduate, because it's a management style as well. Then I would be comfortable putting 2 undergraduates per graduate student. Okay, so there's a little bit of management that I have to do on my end in consultation with my graduate students. So that's typically how I like to do it. So I will have a maximum number of undergraduates in my lab, depending on the number of graduate students as well.
Okay, that's good to know. So if a student at the end of the semester would like to approach you about working in your labs, say starting next semester or the following fall, how should they go about reaching out to you to express that interest?
Just email me. The easiest way to get hold of me is at carl.wallace@usm.edu.
All right, fantastic. Well, I will definitely, at the end of this presentation, put a text box in with your email address so that they can, although you've put it there, that it'll be available for them. And so I just want to thank you for taking the time to talking with our Chemistry 108 students and explaining them to them a little bit about the research that you do.
Thank you for the opportunity, and hopefully I'll see maybe one or two of you in the future.
Sounds good.
Appreciate it.